Hi everyone, in this lesson we're going to be exploring what is a derivative, all the way from the most basic sense that a derivative is a graph of the gradient to a more complicated sense where a derivative is a function that gives the gradient for any x. So first of all, to answer the question I have at the top, we have two ideas about what the derivative is, and one of them is rather easy. That is that the derivative is a graph of the gradient. And that's the way most of us are introduced to the derivative. And it's very easy to understand because if we look over to the right, if I have a very steep line like that, it's going to have a high derivative. And if I have a line that then becomes less steep, the derivative drops. And finally, if I have a line that has a negative gradient, well, the derivative is going to be below the x-axis there. But there's a more complicated explanation or definition for the derivative, and that's that the derivative is a second function. Is a second function. And the notation is f dash x. I'll make that dash a little clearer. F dash x. That gives the gradient slash rate of change in dfx over dx for an x value. And we'll look at that in a second, but basically the first explanation is easy because it's graphical, and the second one deals more with functions. So the first thing I want to say is there are conditions for something having a derivative at a certain point. And we'll write these down on the side here. They're very difficult to understand just in text, but hopefully when we go through examples you'll see how they come into play. And the word that I want everyone to remember from this lesson is smooth. Smooth. Because smooth, although it's not a very rigorous definition or condition, is definitely a good idea to have in your head. If it's smooth, then that implies that it has a derivative. So the more formal conditions are one, that it's continuous, so every point on the graph joins up to the point next to it. Points join up. So you can't have a graph that goes like this. It won't have a derivative at these points, but it will in between. And the second condition is that it's not jagged. So a graph that's jagged like this, although it is continuous at this point, the derivative will not exist at that point. The derivative will exist for these points here and these points here, but not here, here, or here. And the mathematical definitions for these conditions are if it's continuous, if we take the point fx plus h and fx, then the difference between those 2 points should approach 0 as h approaches 0. So this seems rather difficult if you haven't seen it before, but that's basically saying, I'll draw a curve on the left here. If I take a point here, that's at x, and it's got height f of x, and then I take another point x plus h there, so it's just x moving along a little bit, and h can be negative, so h could be in that direction. Then that point has a height f x plus h. So this difference in height, this height here, the difference in height is equal to f x plus h take fx. And if that's troubling you, just imagine this height here was fx, as indicated by this point, and this height here was fx plus h, so the difference is that. And that's saying as I make h very small, which is h tending to 0, then the difference here will also become very small, because this point up here will move further towards the other point until they're basically on top of each other. Now the second condition has a definition, not jagged. That's a little more tricky. I suggest going to watch the video on derivatives first principles, but it's basically saying fx plus h, take fx, instead of using this tends to sign, I'll say the formal limit. The limit as h becomes very small of fx plus h, take away fx on h. So that's saying, cast your mind back to the triangle over here. This length here of the triangle is h, and this height here is fx plus h. So the rise over the run is going to equal the gradient of this line. And when we solve this limit over here, we should get one value, not two. So that's saying the gradient between the point we're looking at and the next point along, either side should be the same. So we'll see how that applies in a second. If you're confused by that, don't worry, keep watching. It'll all be explained. So let's look at an example function. I'll jot it down to the top right. F of x is equal to x cubed, take 6x squared plus 8x, and if you factorize this on the calculator, you'll get x take 2, x take 4. So graphing this, the first thing I recognize is that it is a cubic. So it has the general shape like that. These factors here indicate the x-intercept. So I've got x equals 0, x equals 2, and x equals 4. So I'll mark those in on the graph. 1, that'd be 0, 0, x equals 2, 2, 0, and x equals 4, 4, 0. And now I need to link them up using this sort of shape. It's very easy, just like this. And we have a nice cubic there. Now I haven't marked in the max and mins because that takes a little bit more effort to work out. Let's see if we can graph the derivative on the axis below. Going back to our definition up here, the derivative is a graph of the gradient. And the gradient is basically the gradient of any tangent to a point on this graph. So the gradient here, the tangent is a horizontal line, so it's 0. That also occurs here. So these are generally the first things you mark in on a graph. So I find the best thing to do is take out your ruler, position the ruler so you can see where the gradient for the function is 0, drop a line down, and then mark in on the bottom. The derivative will cut through this point here. It'll be 0 because the graph there has a gradient of 0. You do the same thing for any other stationary points that we find. The gradient is 0 there. So the graph will cut through that point. Now that's out of the way, it's a little easier to imagine what it's going to look like. Here, on this side of the graph, the gradient is very positive. So we imagine the derivative is going to be above the x-axis, somewhere in this region. In this region of the function, the gradients are all negative. So we imagine the derivative function is going to have it's going to have values down there, and then far to the right the gradient becomes positive again, so we expect values up here. Using our derivative laws, if you're struggling with this, go look up the video Deriving Polynomials. we can say the derivative is equal to, take the first term, take the 3 down to the front, 3, and then multiply by x and take away a single power. Take away, multiply the 2 down to the front, so it's 6 times 2, that's 12, and then take away a power, and then add on a to the n because it's 8x. This is a quadratic, and it looks something like this. Now notice, people tend to intuitively grasp the concept of greatest slope. If you were riding a bike down this hill, it's the point where you'd probably experience the fastest acceleration, be the scariest, somewhere there. This is the steepest part of the graph in this region, it has the steepest magnitude. And so it makes sense that it would correspond to the most negative part of the graph. And then on the far left and far right, it shoots up to positive infinity as x tends to infinity, because this does get very steep on the far left and far right. So that's basically graphically what the derivative is and how to draw a derivative from seeing the graph above. Let's see if this function above, f of x equals x cubed take 6x squared plus 8x, actually satisfies the conditions we've laid out on the left here. First of all, is it continuous? Well, visually, we can see that all points join up with the next point along. There's no big jumps. And if we did take 2 points, say f of x and f of x plus h, I'll mark these in x. I've got to get this coordinate in the right order now. X plus h, f x plus h. Then as h got very small, these would move close together until they're basically on top of each other. So there's no worries there. This graph is definitely continuous. And the other thing we've got to think of is this fact down here. Is it not jagged? Well, this graph's not jagged at all. It's all very smooth. And if we took the gradient of, say, this point, we'll take this point here, then the gradient between it and the next point along and it and the point behind is going to be roughly the same. That'll produce one tangent. So now let's look at a much more difficult example, and these tend to pop up both in the multiple choice and the long answer. Just trying to get rid of all these graphs. There we go. Okay, I've got a second function written down here. F of x is equal to. Now when I do this sign here, it's saying it's a hybrid function, so it's going to have different rules at different points. So the first thing I'll say is between the points 0 and 2, it's going to obey the rule f of x is equal to a half x. If this is the first time you've encountered hybrid functions, keep watching and it'll all be explained. Between the points 2 and 3, so x is between 2 and 3, it obeys the rule negative square root x take 2. And between the points 3 and infinity, now I'm just saying x is greater than 3, so that goes all the way up towards infinity, the function obeys the rule x take 4. So the first thing I want to do is mark out 1, 2, 3. Well, 4 is not included. We can have 1, 2, 3. So we've got those points marked in, but I'll take the numbers away just to avoid confusion. Let's try graphing this function. So I'm looking at this particular greater than sign. It's actually greater than or equal to. So I put a closed circle here. Well, actually, a better way to start this off is to say, what would the graph of half x look like? Looks something like this. But we want to confine it only to x being between 0 and 2. So we only want the graph in there. I'll draw it again. There we go. And since it's greater than or equal to 0, I draw a big closed circle here. and since it's less than or equal to 2, I can also draw a closed circle. The second thing I want to look at is what happens between 2 and 3, which will be in this area here. Well, the graph follows the rule negative square root of x take 2, and the strategy I have for this is to say, okay, the square root graph looks like that, the negative square root graph looks like that, and if I translate that 2 to the right, it'll look like this. We'll do it in green. And the point here is going to be 2, 0. And the point here, what happens if I chuck in 3 into this formula? I get negative square root of 3 take 2, so that's negative square root 1, so that's negative 1, so this point down here is 3, negative 1. And I should add here, obviously it's 0, 0, because if you let x equal 0, f of x equals 0. And here, it's equal to, if you let x equal 2, that equals 1. So 2, 1. Now I've actually made a mistake just then. I wasn't paying attention to the greater than signs. It's actually not greater than or equal to 2, it's just greater than 2. So I'm going to go back to this point here and replace it with an open circle. And I'm also going to do the same to this point here until I know what the next value of x is. So now in this region here, going on to infinity, what happens? It obeys the rule x take away 4. So if I let x equal 3, because that's sort of where we are on the x-axis, I get 3 take 4, it's negative 1. Oh look, it's actually this point here, and it obeys the rule x take away 4, which looks something like this, but I only want that region over there. So I say it goes like that, with the point here being 4, 0, because if I want that to equal 0, I have to let x equal 4. So now the whole function has been graphed. And I'm not sure about the examiner's preference, but generally if you want to mark in a point on your graph, you'd use a cross. Circles tend to indicate endpoints, and that is no longer an endpoint, it's just another point on the graph. So using the same method we used before, let's now graph the derivative. Are there any points on this graph where there's a stationary point, so it's a horizontal line? Well, this point is rather suspect. I mean, on a microscopic scale, it could possibly have a little curve like that, but I think it's more likely that it is jagged, so it suddenly jumps up, and we can have a look at that in a second. So there's no stationary point, so I don't expect my derivative to cross the x-axis at any point. What is the gradient for this part here? Because I can take the gradient for some of these values. It's actually 1/2, and we know that because the gradient of a line that has the equation half x equal to 1/2. So I'll put an endpoint over here, and it's a constant gradient, and another endpoint here. Now you'll notice I've put an open circle at endpoints because one of the rules is the derivative does not exist at endpoints. So if I did put a closed circle here, I would lose a mark because you cannot take the derivative at an endpoint. I'll just emphasize that. There we go. Now we ask, what is the derivative for the next part here? Well, it's actually vertical here. So you expect you can't take the derivative at a vertical point, but a vertical function does indicate some kind of asymptote. And we also know that it's actually quite negative. So we expect something starting very negative and then becoming less negative as we move towards this point here. We'll work that out definitely in a second. And then the final part of the graph, this part here, the gradient is going to equal 1 because the gradient of this line is equal to 1. So I can pop an open circle here and I can draw a constant line across. So I'm saying for all these x values here, the gradient of the function is equal to positive 1. Now, what are we going to put in the middle here? I think the best thing to do is to go back to the function and derive it using the laws that we have for derivation. If you don't know these laws yet, go check out the derivation of polynomials and everything should be crystal clear. F dash x is equal to, and it's another hybrid function because it's going to have different derivatives, obviously, for different parts of the graph. So the first derivative is equal to a half, because that's what happens when you derive that term there. And that derivative exists between 0 and 2. But if I were to draw greater than or equal to signs, or less than or equal to, I'd be wrong. So don't do that. This, as it is correct. The next derivative, or we'll skip to the last one, the final derivative is equal to 1, because that's what happens when you derive y equals x take 4 dy dx is equal to 1. And that derivative exists between 3 and I guess we'll put in infinity there. Now, what is going on in between? It's not a straight horizontal line. It's a derivative with a bit of variation. So I think the best thing we can do is write it down just below. It is quite difficult. Y is equal to negative square root x take 2. So what is dy dx? Well, using a bit of a chain rule, it's equal to, you know what, I'm going to put this into a better form. That's negative x take 2 to the power of 1 on 2. So dy dx, I multiply down the half, so it's negative 1 on 2. And then I take 1 off this power up here. So it's x take 2 to the power of negative 1 on 2. So that's equal to negative 1 on 2 square root x take 2. If you've studied the chain rule, that'll all seem a bit simpler. So I can pop that in, negative 1 on 2 root x take 2, and that function exists between 2 and that derivative exists between 2 and 3. So I can mark that in. Starts off heading down towards negative infinity, and when I get to the point x equals 3, well, I plug 3 in here and it becomes negative 1 over 2 root 1, so that's negative 1 over 2. So the final point I get is negative 1 on 2, open circle. Looks something like that. So having used our common sense on this function up here, we sort of knew what the derivative was going to look like, and then by using the formal laws of derivation, we find out exactly what the rules are for this derivative. Now let's look at exactly why I put an open circle first of all here and then second of all down here. So the first condition I have to the left, is it continuous? Well, the graph is not continuous at this point, so of course it can't have a derivative. When people first come across derivatives, they usually say, well, hang on, I mean, as you're heading along this line towards this point, isn't it obvious that the derivative is something like that? But the answer is you have to measure the gradient between this point here and the point along here and the point along here. And the next point along, well, the gradient's just undefined. It's a sudden leap. So this doesn't satisfy the first condition. Now the second point here is more interesting because it does satisfy this first condition. It is continuous, but it is jagged, and the condition is that it has to be not jagged. So basically they're saying, look very closely at this point here, and then using this formula, let's see what the gradient is towards the next point along. And the next point along this way, going along here, the gradient comes out something like that, a positive number. But if h is negative, and in this formula it's fine for h to be negative, it basically means I'm selecting a point to the left in the negative direction. And the gradient between this point and this point is something like that. So it's a negative number. So in effect, that's why I said it has to have one value, not two. Because if it has two values, then this limit doesn't actually exist. Because h has to approach 0 from both sides, therefore the derivative doesn't exist. That is the formal explanation for what a derivative is, and also for telling if a function can have a derivative. I think the key thing to take away from this lesson is that if the function is smooth, then it must have a derivative at the point where it's smooth. But if a function ever has a leap, so it's not continuous, then it doesn't have a derivative at that point, or if it's jagged, it doesn't have a derivative at that point. And the final thing to remember, so you don't lose 2 marks on the graphing question on the exam, don't take the derivative at the end point.